Okay, so we have a projectile problem here that we're going to try and do. The blank for this can be found on the website, but um, if you can just follow along, then that's probably enough for you to get the concept. So what we have here is every aspect of a projectile question that you would be expected. You'll notice that it just simply says a 12 kilogram projectile is shot at 110 feet per second, and it's fired at an angle of 48 degrees from the horizontal where it lands 2 meters above the position where it was fired. So the situation is pretty straightforward then. We have a gun that's shooting a projectile that has a change in height of 2 meters. The projectile is going to have a parabolic trajectory and it's going to land. The gun is going to fire at 110 feet per second, so which is an imperial unit, so we're going to have to convert that. And we know that that can be broken into I hat and j hat components of the velocity, and we're going to have to resolve what that is. We know that we have a value called h max, which is the maximum height of the trajectory, which is not exactly at t1 half, simply because the trajectory is not perfectly symmetrical because it is landing at a different elevation. So the question is going to guide us through the different aspects of what we could hope to find. An assessment generally wouldn't have it broken up this much, but it will kind of give you the algorithm how to go through these problems. So the first thing we have to do is we have to actually calculate how fast this is going in meters per second. So as we do this, we're simply going to write velocity is equal to 110 feet per second times, and here's the conversion that's in the question, 0.3048 meters for every foot, and that gives us 33.53 meters per second. And we're constrained by three significant figures, 33.5 meters per second. And that would be the actual VA, so 33.5 meters per second in the question. So now we have the next part of the question, which is in which part or what parts of this projectile's velocity are in the I hat direction. So when you look at your little right angle triangle that we have, we'll notice that the I hat component is on the adjacent side of the triangle. So we have adjacent side, opposite side, and hypotenuse. So we're going to use cosine for this. So we write V I hat is equal to the cosine of the angle times the applied velocity, or the radar velocities, which I talked about in class. And that's equal to cosine 48 degrees times 33.53 meters per second. And that gives us 22.34 meters per second in the I hat component. So 22.3 meters per second I hat. So that's how fast the projectile will move towards the right here. We'll do the exact same calculation with the j hat one, but the biggest difference is that the vector for vertical velocity is going to be the sine of the angle. So sine theta times VA equals sine 48 degrees times 33.53 meters per second, and that gives me 24.92 meters per second in the j hat direction. So 24.9 meters per second j hat. So now I've really solved all of the. So that brings us to the next part of this, which is actually determining the flight time of the projectile. So we have a particular equation that we have to use. 0 equals negative gt squared plus velocity in the j hat direction. That's the initial velocity. So the second it is shot, how fast is it moving upward? We don't care about the right to left. T minus the change in elevation, or delta H. So that means that the c term in this quadratic equation, because we have ax squared plus bx minus c, so the c term in this will be negative when it's landing above where it's shot and positive when it's landing below. And that's important to remember when you're using your solver. So we can actually simplify this quite a bit. So sorry, there's supposed to be a 1/2 here, negative 1/2 g. We can actually solve this pretty systematically as we always do. So it's always going to be negative 4.9 t squared plus, let's get our j from up here, 24.9 t minus 2. So that is our quadratic equation. So 0 equals, and just so we can see this, ax squared, there's your x, plus bx minus c. So we're in quadratic form, so we can use the quadratic equation to actually solve this. So you can use the quadratic formula, or we could actually just use a quadratic solver. So my first term is negative 4.9. My next term is 24.9. And my third term is negative 2. So I can solve it, and I get 2 roots. So root 1 is 0.0816, and root 2 is 5.00, well, 0.004, depending on how many significant figures you took. This time would be the projectile crossing the 2 meters on the way up, and this time is when the projectile lands. So we can basically eliminate that as a possible route. So we write, and now we have the time of flight. The third part of this equation, or this problem, that I've outlined, is the actual target. So it says a target is located 100 meters horizontally away from the gun at 2 meters above the firing elevation, so exactly where it's going to land. Assuming the projectile misses the target, how high above the target is the projectile when it passes over it? So we have the projectile, and we know how fast it's going to the right. We know that the distance to the target is 100 meters in the equation. So we have velocity and we have distance. So we can write time is equal to the range divided by the velocity in the I hat direction. It is just a grade 10 equation. So 100 meters divided by, well, our I hat speed is 22.3. Meters cancel, seconds are on the bottom of the bottom. So we can actually make sure our unit comes up in seconds. And we have 4.48 seconds. Now we go back up and we use this equation, but we don't actually put anything in for h. So we're going to put this t in for it, and we're going to solve for h. So I have the exact same equation as before, except h is now on the left-hand side. And don't forget my square. So h is equal to negative 4.48 seconds squared plus 24.9 times 4.48. Making sure you don't forget your negative sign here, because that will give you a really, really big number, and that happens a lot. We end up seeing that we are 13.10 meters, and that 13.10 meters is in reference to above where it was shot. So it's going to be 2 meters. The land is 2 meters higher up here than it was down there. So we're going to take 2 meters off. So the projectile will be 11.1 meters above the landing position. Finally, we have the question that's frequently asked is, what was the maximum height of the projectile? This is generally done in math class a lot, but we just have a very simple equation. The negatives have already canceled out of this. I'm going to make g positive because its negative has canceled with the negative vj squared. So this is the initial vertical velocity the second it was shot. And this, of course, is acceleration due to gravity. We're not going to worry about a negative in this case. So we write in our vertical velocity, it's 24.9 meters per second, all squared, over 2 times 9.81 meters per second squared. My seconds is squared are going to cancel. One of my meters is going to cancel, leaving my final unit with meters, which is exactly what I want. And I end up with 31.6 meters. And this solution is above the position that it was fired. So it's 31.6 meters above where it was shot, or 29.6 meters above where it landed. The question really hasn't asked me which reference point I'm using, so either would have to be acceptable in this case. And we 31.6 meters, and we put our value in, and that is how we do a projectile problem.